Good afternoon, folks. So, let's see. How many of you start playing with that? So, let's see. Your tests, I've got to go through still and do the partial credit. So, expect those to change this afternoon to updated scores. Can you guys see those scores as they are? Okay. But don't let them distress you if they're lower than you thought they were. I'm going to go in and look at your scratch work and so forth and be able to add some points to those. Let's see. I wanted to check those. Looks like some of you have had a chance to start playing with the chapter 4 stuff, which is great. Looks like about half and half. Let's see, you have some questions on the polynomial stuff you've been playing with? Anything particular you want to talk about in there?
I think maybe it'd be interesting if you talked about like where synthetic division comes from.
Okay. That's starting to get into 4.3. Yeah, certainly. Just to give, before we do that, I certainly will, but just to give a little spiel on polynomials, one of the big things to focus on there is the vocabulary, so things like degree and lead coefficient and lead term and those vocabulary bits. But the section on end behavior is fairly important. So if we're looking at a polynomial that's, say, negative 5x to the third minus 2x squared plus 4x minus 1. This polynomial's got all kinds of twists and turns to it. We can look at it and say it's third degree, which will mean it has 2 turns or as many as 2 turns and as many as 3 x-intercepts. Could have less. But the idea of end behavior is a fairly important one. So the idea that the fact that it's odd degree means its end behavior is going to be pointing in opposite directions. So odd degree means we're either going to come from the bottom and then turn as much as we turn and then leave upward, or it's going to come downward, turn as much as it turns, and leave downward. Essentially, if you're an odd degree, you're either generally increasing with some wiggles in the middle or generally decreasing with some wiggles in the middle. So how we tell the difference between those two is that sign of the lead coefficient. That's why it's referred to as the lead coefficient test. Though I always thought it should be called the lead term test, but nobody asked me. So the fact that this lead coefficient is negative means we're going to be generally decreasing. So this function is going to come down out of quadrant 2, wiggle as much as it's going to wiggle, and then leave outside in quadrant 4. As opposed to if we had a polynomial that were, say, 5 plus 3x squared minus 2x to the third plus, I don't know, 5x to the 6th. The fact that this lead term Again, that's the lead term because it's the one with the highest degree. It's the one that's in charge. So that lead term is a 6th degree, so it's even. That means our end behavior is either going to be up and up, or it's going to be down and down, kind of like a parabola with some extra wiggles. And again, what's going to tell us whether it's upward or downward is going to be the sign of that lead coefficient, the coefficient of the lead term. So because it's even and positive, whatever the x-intercepts are, wherever our turns are, we know it's going to do whatever it's going to do, but its end behavior is going to be upward and upward. And you'll often hear that or see that written as x heads towards infinity. That means as x goes in this direction, f of x does what? Well, as x goes towards infinity, the f of x values, the function values, the y values also go up towards infinity. Where here in this function, as the x's went towards infinity, as we went in this direction, the function values went towards negative infinity.
I feel bad for interrupting, but would
please.
it be possible for me to record the lecture?
Oh, actually, it is being recorded right now.
Oh, cool. Never mind then. Sorry.
And I'm going to post it, but you can record it also if you want anytime.
I forgot that they were going up on my open math, so I'll be fine. Thank you.
Sure. What was I? Oh, so you'll often see this notation for in response to the end behavior. Similarly, here as x goes towards negative infinity, as we head that way on the graph, here the function heads towards positive infinity because the function is going towards arbitrarily large positive values. Over here, the same thing's happening. As x heads towards negative infinity, the function is heading towards positive infinity. So you'll see this notation often for, or when they start talking about end behavior. Questions about that? Some of you have already kind of been playing with that, but that notation is going to come up every now and again. So I want to make sure you're happy with that. Heading toward talking about division, one of the things that's we're eventually going to want to be able to do is find these x-intercepts. And ideally find these max and min, these turning points as well. Unfortunately, finding those turning points is more of a calculus question. It's one of the big things you'll do in calculus. But being able to find these x-intercepts is something that we want to be able to do algebraically at the stage we're at, to the best of our ability anyway. And one of the ways you're kind of used to doing that is if we have a function, and let's say it was, just a nice x squared minus 2x minus 8. And I said, find x-intercepts, you would respond in one of a couple different ways. From our last discussion and from your background, you know that x-intercepts happen when the function is equal to 0. So we should be responding by setting that equal to 0. But the kind of, well, then what do we do? There's a couple different responses. We could complete the square, certainly. We're not going to, but we could. We could use quadratic formula if we wanted to, But what was the thing we should be trying to do first with any of these? Before quadratic formula, before any other tool. What's a good tool to try first?
Completing the square?
Completing the square is a good tool, but even before completing the square,
Is it just factoring it out?
it's just factoring.
Yeah.
Yeah, if it's nice and factorable, we should factor it before we use any of those other tools. Now, again, this is going to, I mentioned this before, this is going to depend on what your factoring skills are like. If your factoring skills are nice and strong, you'll be happy with that step. If your factoring skills are not terribly strong, then you need to strengthen them. Thus, whether you enjoy the step or not, it's even more important for you to try to factor it because you need to work on those factoring skills. So if we're able to factor it, then solving it becomes quite nice because as soon as we have it as a product, that zero product principle takes over. And we know that it's going to be true whenever the parts are equal to 0. So we get a nice couple of solutions. And then, of course, there is the OR quadratic formula. Now, the issue is we are going to be trying to do the same thing with higher degree polynomials. We want to be able to do this same kind of thing with, say, third degree polynomials. I want to be able to take a third degree polynomial and find its x-intercepts. Well, the first thing that doesn't work is that quadratic formula. That quadratic formula is specific for quadratics. So the quadratic formula falls away completely. You might ask, well, is there a similar formula to the quadratic formula for third degree polynomials? And frankly, yes, there is. It took an extra several hundred years to be developed. And actually, its development led to a big change in how we think about complex numbers. And if you were to write the quadratic formula out, and the quadratic formula was, say, about that long, the formula for third degree polynomials would probably fit in that box. It's a huge, 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 huge formula. The one for fourth degree polynomials would probably fit in that box. And it's no fun. And there isn't one for fifth or higher. And actually, the one for fourth degree polynomials has only come about in the last couple of decades. So the idea of, well, hey, for finding intercepts or finding x-intercepts for polynomials, can't we just use the formula? Only a couple have formulas, and those formulas are terrible. So relying on ideas like the quadratic formula and thus like completing the square is not going to be helpful. We really do need to depend on the idea of factor. But looking at a second degree polynomial and realizing how it's factorable is hard enough. Looking at a third or fourth or fifth degree polynomial or sixth degree polynomial, we will be factoring sixth degree polynomials in a couple of days, by the way. Just looking at it and going, oh, I should factor it this way is terribly difficult. So we need to take this process of factoring and find a way to break it down into nicer tools.
Come here.
And that's essentially a main part of the goal of chapter 4, is to be able to do that. So if we want to get better at factoring, or better at the idea of factoring, it might be good for us to back up and look at, okay, what is factoring? How does factoring work? And to do that, let's recall how we factor a number. So if I want to find the factors of, well, sure, factors of some number like 51, if I asked you what are the factors of 51, what would you do? Now you probably look at it and say, well, gosh, what goes into 51? 51 is kind of a weird number. It's not even, so it's not divisible by 2. So 2 isn't a factor. You might look at it and say, well, 5 can't be a factor because it doesn't end in, it's not 55 or 60. It doesn't end in a 5 or a 0. If it's not divisible by 2, it's not divisible by 4 or 8 or any other multiple of 2. Could it be divisible by 3? Now you might not know, but there is a nice handy rule for divisibility by 3. If the numbers add up to something that's divisible by 3, then the whole number is divisible by 3. So the fact that 5 plus 1 is 6, and 6 is divisible by 3, means 51 has to be divisible by 3. So 3 has to be a factor. That tool actually works for 3s and 9s. Doesn't work for anything else, but works for 3s and 9s. Okay, technically it works for 27 also, but nobody uses it for 27. And 81 in any power of 3. So this number should be divisible by 3. But if we wanted to find out, one, is it really divisible by 3? And more importantly, find what else its factors are. So like 3 times what would you do with this 51 and that 3 to, 1, prove that they're divisible, and 2, find out what the other part of that multiplication is? Well, ideally, to find that out, you would go and divide them, right? If they divide cleanly with no remainder, that means 3 is indeed a factor. And the result, more importantly, the result of that division is going to be the other factor. So 3 goes into 5 once. Remainder of 2, bring down the 1. 3 goes into 21 7 times. 3 times 7 is 21. Subtract those, we get the 0. No remainder. Great. 3 times 17 is 51. So what are the factors of 51? 17 is nice and prime. 3 and 17 are. So the process of factoring things should involve this idea of division. Fair? So if we have a polynomial, say, x to the third plus 2x squared minus x minus 4. And we want to see if something's a factor, so given that polynomial is, say x plus 2 a factor, we're going to do the same thing as we did with, is this 3 a factor of 51? We're going to divide them. And frankly, we're going to divide them in almost exactly the same way we divided the 3 into the 51. We're going to take the x plus 2 and divide it into the x to the third plus 2x squared minus x minus 4. Ideally, you've done some polynomial long division in your background somewhere. How many of you have done some polynomial long division somewhere in your background? No one's happily going, yay, and it was so much fun, but you guys are all kind of going, yeah, maybe a little bit. It is a little bit weird. It is a little bit notationally heavy. But the nice thing is, in some ways, it's frankly even easier than dividing numbers. Because all we have to focus on is those lead terms. You know, so here we asked, you know, what do we multiply by 3 to get close to that 5? And we look at it and go, well, I'd like to multiply by 2, but multiplying by 2 is too much. So I'm only going to multiply by 1, and we'll have that, you know, 2 left over, right? When we make choices in polynomial long division, if we only focus on those lead coefficients, we never have to worry about getting close to something. We can get exactly on values. So for example, what do I have to multiply by x to get x to the third? Well, we can multiply by x squared, right? That's going to give us exactly x to the third. And just like up here, when we did numeric long division, we multiplied that 1 times the 3 to give us that 3. Okay, so x squared multiplied by the entire x minus, or x plus 2, sorry, is x to the third plus, let's see, what, 2x squared. No, that's going to give us a 0. That's fun. And then what did we do with the 5 and the 3? We subtracted them. So what are we going to do here? We're going to subtract those. X to the third minus x to the third is 0. That column should always 0 out. The 2 minus 2 also gives us a 0 by kind of coincidence. So 0x squared, and I'm actually going to write that 0x squared because I want the placeholder minus x. Okay, so what do we have to multiply by x to get 0x squared? That's a weird question. We can multiply by 0, but frankly, I want to consider multiplying by that 0x. I want the placeholder. I'll leave it out later. But having everything line up and keeping all those placeholders is really handy. So 0x times x is 0x squared. 0x times 2 is 0x plus. And we're going to subtract those. Again, everything goes away there. Negative x minus 0x is still negative x. And then we're going to bring down that 4. And we just keep asking the same question. What do we have to multiply by this x to get that negative x? Well, we'd have to multiply by negative 1. That's going to give us, when it multiplies back, negative x minus 2. And we have to subtract those. These go away. And then negative 4 will turn into a plus 2. Negative 4 plus 2 is negative 2. That's a remainder. Since we got a remainder, we could write this as plus negative 2 over x plus 2 if we want to write out the result of the division. But the question of, is x plus 2 a factor of that polynomial? Is x plus 2 a factor of that polynomial? Yes or no? Seeing no's, it didn't divide out clean, right? That 3 was a factor of the 51 because we got a remainder of 0. Any other remainder would have told us it's not a clean factor. So is x plus 2 a factor of that polynomial? No, it's not. So dividing polynomials in general is going to allow us to test and find factors. Just the same way dividing allows us to test and find factors in division. Let me give you one here to practice. Say is, how about x minus 2 a factor of, let's say, x to the 4th plus 3x to the 3rd minus 5x squared plus 6x minus 8.
So I have a quick question.
Shoot,
Can you hear me?
yes.
Okay. So I've been working on the homework that's due tomorrow. And there are a couple questions I'm confused about.
Okay.
One of them appears to be similar to what we've been working on so far. It's number 3 on 4.1. It has a graph that's shaped like that.
Mhm.
And it doesn't give you an equation, but it is asking you to find the relative maximum, relative minimum, increasing and decreasing, the domain, and the range. But there's no equation. And
Right.
on the video that's attached, it has an equation already. So how would we find the equation?
We wouldn't.
Then how do we find the info?
By finding these coordinates from the graph. So for example, if you look at your graph and can tell that this point is, say, the point 5, -3,
Mhm.
and this point is the point, say, -2, 10,
Yeah.
that means your relative max is at -2. Your relative maximum value is 10. If you're just asked what is your relative maxima, it's the point -2, 10. Your relative minimum is the point 5, -3.
Okay.
Do be careful if you're asked where is your relative minimum. Where is always an x value question. So where is it happening? Your
Okay.
minimum is happening at 5. What is your relative minimum value? The value is -3. But if you just ask generically, what is the relative minimum point of that graph? It's the point 5, -3.
Okay.
Then where are we increasing? It's always, it's a where, so it's an x value question. We are increasing from -infinity until we reach that maximum. So your increase would be from -infinity until you hit that -2. And unioned with, we're increasing from 5 to positive infinity. So we're increasing here and we're increasing there. So we're
Okay, I'm
increasing.
wondering because for the relative minimum, when I try to plug in what appears to be the answer, it says this is not a decimal or integer value. So how would we find that?
Well, let me see exactly what it's asking you here. Oop, that's not what I want. So 4.1 number, you said 3?
Yes.
Number 3. So when it says the function has a relative maximum of, that's the maximum value. So looking at that graph, your relative maximum has a maximum value of 2. at x equals, looks like, well, mine says -5. I don't know what yours says. So let's show you mine here. So that has a relative maximum of, that of is the value. So here that maximum has a maximum value of 2
Okay.
at x equals what looks like -5. So check it.
Oh, okay, okay.
And that's what I was saying about being careful about is it asking for the point? Is it asking for the value, or is it asking for the location? You know?
Yeah. So that would be okay.
Fair.
Yeah. And then with the function is increasing, do we do a U or a comma between the values?
It should be a U. Yeah,
Okay,
nice capital U.
just wanted to make sure.
Mhm.
Alrighty. Sorry, I've been working on this for a couple of days and I couldn't figure out how to do it.
Well, as I said, a lot of it's that vocabulary with the of and at and where and what,
Yeah.
you know, and that can be a little bit weird. But one of the things I often relate it to is you can imagine if somebody asked, you know, what's the most we lost this year in a single month? And somebody said, okay, what's the most we lost this year in a single month? And somebody says November. Yeah, that's not the right answer to their question, right?
Yeah.
And that's kind of what this is, as opposed to somebody asking, you know, what month did we lose the most? $10,000.
Yeah.
They're talking about the right thing, but they're talking about different parts of it. So that's what the kind of, at, where, when questions come into play.
Yeah.
Cool.
Yep.
Yeah, and as I said a little bit earlier, finding maximums and minimums, really finding those values from an equation is really, frankly, a calculus question. Even if we had the equation of this curve, trying to figure out those maxes and mins mechanically is a calculus question. It's not a terribly hard calculus question, but it is a calculus question. For us, it would be, even if I just gave you an equation and said, what's the max? You would graph it and find the maximum on that graph, you know, just using your tools or just looking at it, because that's all we got right now. So did you guys decide whether it was a factor or not? Or were you listening to me talk? You're probably listening to me talk. I am fascinated. So do you guys want a couple of minutes to go through that division by yourselves, or do you want to go through it together? Or do you want to silently stare at something until I decide which one you're going to do anyway? What was that, Julia? Your mic went off, but I can't hear you.
Can you hear me now?
Yes.
Okay, sometimes my computer audio goes really weird and like some people can hear me and some can't. Can we do it together?
Sure.
Okay.
So if we look at the x minus 2, and I will get to the connection with synthetic division next, Amy. I didn't forget. And we want to divide that by the x to the 4th minus 3x to the 3rd minus 5x squared plus 6x minus 8. And again, if it's a factor, the division will come out clean with no remainder. And we will be left with not only knowing that the x minus 2 is a factor, but we will be left with a third degree polynomial that is also a factor. Just like when we divided that 3 out of 51, we also got the 17 was a factor. So if it divides out clean, we're really happy. If it doesn't divide out clean, okay, we know something that's not a factor. Great, we'll then go try to find something else that might be a factor. But the way we do this will always kind of be that same question. We will focus on those lead coefficients and ask, what do we have to multiply by this x to get that x to the fourth? Well, x times x to the third will give us x to the fourth. And you might notice I'm writing it under or on top of that x to the third column. I'm trying to keep my place values all lined up. That's one of the reasons, like in the example above, why I kept those zeros in there. It's just to keep everything lined up. Our division algorithm is very based on kind of positionals. So it is nice to have those things lined up. Now, when we do our actual multiplication, we have to remember to multiply that x to the third by our entire divisor. So that x to the third times x is our x to the fourth. And then our -2 times x to the third, -2x to the fourth. And just like our normal division, we then have to subtract those. Now, this subtraction is where most of the errors happen when people are doing polynomial long division. They forget that subtraction. Because we do have to do this +3 minus -2, and +3 minus -2 is 5. So do be careful with that subtraction. Some people like to write the negative distributed. I like the negative and then the parentheses to remind me to distribute. However you want to denote that for yourself is fine, as long as you're remembering to do that distribution. But then we bring down the next one, -5x squared, and continue. What do we have to multiply by x to get our 5x to the third? Well, we'd certainly need a 5, and we would need an x squared. And notice it automatically kind of lines itself up. Our 5 times x squared, or sorry, our 5x squared times x is going to give us that 5x to the third that we wanted. Our 5x squared times -2 is going to give us a -10x squared. We then have to be careful of the temptation to have that turn into a -15, because remember, we are subtracting those. So -5 minus -10 is a +5x squared. And plus 6x. So again, back to our question. What do we have to multiply by x to get 5x squared? Well, we better multiply by a 5x, just x to the first this time. That's going to give us the 5x squared we want. Good. And a -10x this time. And we have to subtract those. So 6 minus -10 is going to be 16 x's. Bring down that -8. What do we have to multiply by x to get 16x? Well, we need a 16. And that's going to give us a 16x minus 32, unfortunately. Well, unfortunately, assuming our goal was to have a factor. And that's going to give us a +24 as a remainder. So no. x minus 2 is not a factor of that. I tried to make up numbers to make it a factor, and I was off by that multiple. So I tried, but so it takes a little bit of practice. It is a fair amount of writing, but it really does follow our algorithm for normal numeric division quite well. There's a nice reason why, by the way, and I want to show you this. Hopefully this won't drive you too nuts. But let's say we want to divide 12 by, say 4,823, and we want to divide those. We know how to divide those. It's not polynomial long division. It's just numeric division. You'd ask, what do you have to multiply by 12 to get 4? You can't. What about 12 to get 48? And you'd go through your process, right? But I want to write these in expanded form. That 12 is 10 plus 2, right? And that 4,823 is 4,000 plus 800 plus 20 plus 3. That's what that notation means. We're so used to looking at 4,823 and knowing it's 4,823 by the position of all those numbers. But mathematically speaking, that's actually a fairly new convention. It came out of India a couple hundred years ago, a couple thousand years ago, 12, or it doesn't matter. So it's not that old. So we could do our division this way too. We'd ask things like, well, 10 goes into 4,400 times, and we could do it that way if we really wanted to. We don't want to, but we could. This 10, by the way, that's 10 to the first power plus 2. And this 4,000 is 4 times 10 to the third, right? Plus 800 is 8 times 10 squared, plus 2 times 10 to the first, plus 3. Well, if I let those 10s be something other than 10s, isn't this x plus 2 4 times x to the third plus x, or 8x squared plus 2x plus 3? Frankly, every number you've ever looked at is a polynomial with an x value of 10. Then added together. So a lot of the tools that we're used to, well, this is a tool for numbers, not for polynomials. All numbers are polynomials. They're just simple ones. So the tool that we use to divide this should really be able to be similar to the tool that we use to divide that. It's just we remove a tremendous amount of the notation for it. Fair? Now, speaking of removing notation, Andy, you asked about the connection between, synthetic division and all of this, right? Well, one of the things that's going to be a little bit, or could be a little bit of a problem, is we are going to end up in a position of having to factor lots of things and having to check a lot of factors. So if we had to do all of this work every time we wanted to check to see if something was a factor, that would become super irritating super quickly. So it would be nice if we had a way to speed this process up. So how could we speed this up? Notice as we did this, this x to the fourth minus x to the fourth, well, this part always worked out. If that part is always going to work out every time, as long as we make the right choices, do we have to write it down? Let's not write it down. And the fact that this is an x to the fourth, x to the third, x squared, x to the first, and a constant term, as long as I agree to always put my coefficients in order, could I get away with not having to write that down? I'd have to make sure everything's always in order. But if I'm always in order, I could get away with not writing that down. The only thing that's really important in this division process is this subtraction, and that subtraction, and that subtraction, and that subtraction. Those subtractions are what moves this process forward. Fair? So what our process of synthetic division does is it takes this whole process and abstracts it, just writes it in a way where, just looking at it, you wouldn't recognize what you're doing, but allows us to track the important calculations, the important multiplications and subtractions, while not having to write all this other gobbledygook down. Now, the advantage of it is going to be speed. We're going to be able to work a lot faster. The disadvantage, anytime you abstract something, the disadvantage is generally if you don't know what you're doing, you can't do it. If you're not sure how to polynomial long divide, the notation allows you to kind of keep straight what you're doing. When you take away notation, you take away that help, but you gain speed. So what synthetic division does is it takes away all the notation for the purposes of speed. So how do we do it? Well, if we want to do synthetic division, if we want to perform this division, either to check to see if something's a factor or any other reason we might divide stuff, synthetic division is going to track the important values. We need to know this polynomial. But again, as long as we agree to be in order, all we really need to track are the coefficients. So the coefficients there are a 1, a 3, a -5, a 6, and a -8. And the only reason we know that this -5 is an x squared is because of its position. Because this should go constant, x to the first, squared, third, fourth. So very important that we're in order. Also important if there's any missing, like if there was no x to the third term there, imagine this term wasn't there, we'd have to put 1, 0 x to the thirds. -5, 6, -8. Fair? So do be very, very careful about that. We have to make sure any 0 placeholders are put in there or this process won't work. So we're going to take those are our coefficients. And we're going to divide by, well, notice again, this x, we really didn't do anything with it other than track it down. What was important was this 2. That's what made all these subtractions work. And of course, all of those subtractions, we, because we subtracted them, that -2, all those negatives turned into positives, right? So instead of using that constant, that -2, what we do to make the process easier on ourselves is we take that x - 2 factor and we take its root. The root there would be +2. The root is what makes it 0. And it's also called, if you want, the 0 of the factor. It's also the x-intercept that this factor would represent is a positive 2. So instead of taking that constant, that negative 2, we take the root or the 0 of the polynomial, that positive 2. That will allow us to not have to subtract. And we put it in this structure with an extra line underneath. Leave yourself space in between there, but an extra line underneath. And we use this structure to perform all the important operations of our division. And again, the goal is speed, so this process should be nice and fast. That lead coefficient, that 1, is just going to come straight down, be a 1. And then through the rest of the process, it's all going to be multiply, add, multiply, add, multiply, add. So 2 times 1, 2 times 1 is 2. And then add those together, we get 5. 2 times 5 is 10. Add those together, we get 5. 2 times 5, 10. Add those together, we get 16. 2 times 16 is 32. Add those together, 24. Put in a little box. That 24 is a remainder. For that to have been a factor, that remainder should have been 0. It's not a factor, so the remainder isn't 0. But notice that's the same remainder 24 we got down here. Also, this polynomial here, the 15516, is our 1x to the third plus 5x squared plus 5x plus 16. So we still got this polynomial out and our remainder because we tracked the same calculations. This 3 minus negative 2, that was our 3 plus 2. The negative 5 plus 10, negative 5 plus 10. The 6 minus negative 10, so the 6 plus 10 we got there. It's the same calculations. Just isolated from all this notation so we can have it happen very, very quickly, so we can test to see if it's a factor very, very quickly. That seem reasonable? Very handy tool because it is very fast. It does have the disadvantage of we have to know what the pattern means. We have to know to be multiplying and adding, multiplying and adding, multiplying and adding. We have to know what this remainder represents, that it's a constant, x to the first, x squared, x to the third. If we don't know that, we can't use the tool because there's no notation helping us know what things mean. Fair? Gosh, the speed is so handy. Let's say we asked, is x plus 4 a factor of x to the third minus 5x squared plus 6x minus 24? Well, we could do the polynomial long division. Doesn't take more than a couple minutes really, but it does add up. Or synthetic division. 1, negative 5, 6, negative 24. With the root of this is a negative 4. Bring down that 1, negative 4, negative, add them together, negative 9. That's going to be a 36, positive 36. Add those together, 42, negative 4 times 42, negative 168. So like not 0, whatever it is. So is x plus 4 a factor of this thing? No. I promise eventually we'll deal with ones that are factors. Just, it's hard to make up a large polynomial that happens to be a factor. We could do it up here though. I had that one up there. That, so is x minus 1 a factor, I should say x plus 1, sorry, is a factor, is that a factor of x to the third plus 3x squared plus 3x plus 1. Again, we could do polynomial long division, or 1, 3, 3, 1. That thing's root is a -1. Bring down the 1. -1 times 1 is -1. Add them together, get 2. -1 times 2 is -2. Add them together, 1. -1 times 1 is -1. 0. So yes. And not only yes, but we know that it's x plus 1 times this polynomial, x squared plus 2x plus 1. So not only did we test the factor, but the fact that it broke it down told us another factor. And if we could keep doing that, we could break it down all the way. And frankly, this being a quadratic, we know how to factor quadratics. And boom, we factored the third degree polynomial. So Andy, does that answer your question about what the connection is for synthetic division? It does have another cool property, by the way. If you had this function, this f of x equals, and I do want to leave you with this today. So do this. But if somebody gave you that function and said, find that function evaluated at 2, your natural response should be plug that 2 in for all those x's, right? Not hard to do, certainly doable, but it's a little bit of a process. Take a moment and do that. Plug that 2 in for those x's and find that value f at 2, either by hand or use your calculator or whatever tool you'd like. You went to lunch with your family. What did you bring me? Put up in the chat what you get when you evaluate that at 2. When you're done with that, or if you're done with that already, do it for f at 4. Andy, you said you got 24 for that? Does anyone think that's a coincidence? That was the function evaluated at 2 is the remainder when you do synthetic division at 2. Guess what you're going to get for f at 4? Well, if we'd have actually done this, we'd have gotten what, negative 192? Yes, Clark, of course. So is that negative 192? Anybody calculate that out and find a negative 192? Yes, no, maybe, unsure. Didn't get 192? Did I do something wrong in my synthetic division? Oh, sorry, you'd have to put it down into this function. Sorry. Call it G at 4 for that function, G. Sorry. So what about that? Did that work? Yes, no, maybe? No? Let me check my synthetic division. Oh, crap. Should have been negative 4. That's what I get for trying to rush at the end. Anyway, if you do it properly, the result of synthetic division is the same value as you get from evaluating the polynomial at that value. Don't rush at the end. So, but it does give you a very nice way to quickly evaluate polynomials. That's very useful. Maybe I should have gone with a new polynomial. So if you're given something like even just x squared plus 5x minus 10, and you want to evaluate that, you want to find that where x is equal to 2, you do synthetic division with the 2 really fast. 2, 7, 14, 4. And that's evaluating that the same thing you should get. Times 2 minus 10. That would be 2 squared plus 10 minus 10 is 4. 4. Same value. Very nice way to very quickly evaluate polynomials. Always irritates my calculus students. We evaluate a lot of polynomials in calculus, and I'll just write this down and tell them it's 4, and they'll be like, how did you do that? I'll say, I had you in 111, you know how to do that. And they will shyly slink away because they don't remember. Okay. By the way, that tool is called, your textbook does talk about that. It's called the remainder theorem. The fact that the remainder with synthetic division is the polynomial evaluated at the root. So it's a nice tool. My being off about the negative notwithstanding, it's a nice tool. Okay, anything I can do for you guys before you take off? I'm gonna hang around and answer some questions for Clark, but anything else you guys need before that? Okay, if something comes up between now and next time, let me know. If not, wander off and have a wonderful day.
Thank you. Have a good one.
Thank you.
What can I do for you?
Okay, hi.
Hi.
So I am working on 4.1 still,
Mhm.
and I'm on question 4, which is the other one I was kind of struggling with. And I don't really understand what it's looking for. I have the graph.
Okay.
It didn't show up right on my calculator, so I went to another site and graphed it. And it's kind of weird. It's the equation of f of x equals the square root of 2x cubed plus 7x squared.
Okay, so yours has a 7. Okay.
And
And what did that graph end up looking like?
it looks kind of like a whoosh.
Like a whoosh. Okay.
Yes, it is. It's an arch in the negative second quadrant, and then it goes down at 0 and then extends upward to infinity over 4 spaces.
So like that.
Yeah.
Okay.
Or, I guess 3 spaces. Yeah. let me look. No, wait. It just extends upwards at infinity,
Okay.
basically.
Okay. So when you're trying to find the local maximum, you're trying to find that value.
Yeah, I thought it was negative. Oh, I guess that's 2. Is that 2? Yeah, it is. Okay, so that's why that's wrong, hopefully. And then x equals. Yeah, so I don't really understand what I'm doing wrong.
All right, well, let me grab yours particularly so I can look at what you're looking at.
Yeah, I mean, I could share my screen if you want me to, but
That's okay. Well, you're asked to be accurate to 3 decimal places, so you would need a couple more decimal places than that.
okay.
So one of the things, say, it does ask you here to use the calculator, right?
Yeah.
And it's not just saying use the calculator for the graph. It's saying also use the calculator to find those values, because your calculator does have a tool for finding mins and maxes. Well, you can tell it to look in this area and tell me what the maximum value is, and it will output what those maximum values are. And you might not have used that in the past. Have you used that in the
no,
past?
I haven't.
That's not a problem. If you go to RCC under faculty and departments and the math department. So the main RCC site. And then right here is faculty and departments. You can just search for the math department too, but go under faculty and departments and then scroll down to the math department. Down here near the bottom, I've placed some videos. One of them is min, max, and intercepts. That is a nice little video that somebody made. Oh, that's very loud. That will go through how to use the calculator to find those maximum values, those minimum values. And, so it'll tell you how to search those out and have the calculator. So if I can show you an example. Go ahead.
So on the math page and like the mathematics, and it has like a picture of a class and yeah. So
And then if you scroll down a bit where it says graphing calculator help,
yeah.
there's one that says max min intercepts.
Okay.
That tool will walk you through finding those mins and maxes with the calculator so that it will output like what that minimum and maximum, or what the XY coordinates of any point you want there is. Oh, you're breaking up. What did you say?
I said okay.
Okay. So watch through that. If that helps, great. If it doesn't, let me know and I can help you with it.
Okay.
But yeah, just being able to kind of look at the graph and say, oh, that's at about 2 and that's at about 3.5 is fine, but it asked for more accuracy than that. And frankly, it did that because it's trying to make sure you guys know this tool. So just,
Okay. Alrighty, sounds good. And then
Okay.
let me see. Let me go back. So then I don't know. The local maximum of blank at x equals blank is still really confusing to me. And the whole increasing and decreasing thing, I don't really understand.
so one of the things to keep in mind when it's increasing and decreasing, there's some language in there that's kind of left out, unfortunately. When we say where is the function increasing, there's some kind of hidden qualifiers on that. If we get kind of expanded this sentence, it would say for what x values, that's kind of intrinsic to the where, but for what x values.
It's just x values?
Yep. Are
I didn't know that.
The-
Okay.
y values,
Oh, that's frustrating.
the function values,
So then decreasing would be y and
Nope.
increasing would be x?
they're both x.
They're both x. Okay.
Yep. For what x values are the y values increasing as the x's increase? Now, if it asks where's the function decreasing, the only thing that changes is this increasing to decreasing. So essentially, if you've got some graph here, some function, you're asking, as we go this way along the number line, as our x's go in that direction, what's the function doing? What are the y values doing? And it sounds silly, but one of the things I often use is imagining a little hiker.
Okay.
As that hiker goes in this positive x direction, when is that hiker going uphill versus when is that hiker going downhill?
But it's all in the same line.
Along that graph, yeah.
Okay.
So the hiker is going uphill for x's from, in this case, negative infinity up until whatever x value that happens at, say -2.
Okay.
And then they'd be increasing from this, say that's at 4 on. Fair? If you were asked, when's the hiker going downhill? When's the function decreasing? They're decreasing from here down to there. So the x values that are making it decrease are between -2 and +4.
Okay. And then when it was increasing again, would it be 4 to infinity?
Yep.
Okay.
And it often helps, like our conversation before, to think about it in terms of time. So as opposed to where, maybe when is the function increasing? And if this axis was time, you'd be increasing from the beginning all the way until this time period. And then you'd be increasing from this time period on.
Yeah.
So sometimes kind of thinking of it more in terms of time than location can help. But yeah, it's all about this where is x values such that the function, the y values are doing something.
Okay. But in order to find that, I have to find the maximum and the minimum, right?
Right, because that's where it changes.
Okay. Alrighty, sounds good.
Okay,
Thank you.
sure, no problem. Anything else I can do for you?
I think that'll be it.
Okay. If anything comes up, let me know.
Thank you.